Hey guys, welcome once again. As you know, there are a lot of isolated type of topologies of SFPS. In this video, we'll see about the working of push-pull DC to DC converter and its design steps. The push-pull converter is one of the oldest topologies and it can give multiple outputs, which gives isolated DC voltage from input. Output voltages can be higher or lower than input voltages as we change the winding of the transformer. The relation amongst them is shown by the ratio of input voltage upon output voltage is equal to number of primary turns upon number of secondary turns. Now let's see the circuit diagram of this converter. A pure input voltage is given at the input side. It contains two active switches as transistor, let's say MOSFETs, a center tap transformer, two passive switches as diode, an LC filter, and a feedback is given to the switches to regulate the output. The MOSFETs are alternately switched on and off. The sources are connected to the ground. There are three leads at the primary side of the transformer. Two of them are connected to the drain of the MOSFET and center one is connected to the input terminal. At secondary side, two leads are connected to the anode of the diodes and middle terminal is grounded. Cathode of both diodes are connected to LC filter. This is the general circuit diagram of the push-pull converter. Now we'll see the working. We'll split its operation in two different forms and it will become easier to understand. That is when Q1 is on and when Q2 is on. We'll make four parts of the transformer, just considering they are like inductors. That is, on primary side this will be L1, this will be L2, and on secondary side this will be L3 and last will be L4. Initially, supply is given at the input side and at first half cycle of the switching frequency, the transistor Q1 is turned on. Then L1 gets charged up to input value and due to induction of voltage, L3 and L4 will get charged too. In this case, direction of the current will be clockwise. Due to that, diode D1 gets forward biased and D2 will be reverse biased. This voltage is in pulsating form. Hence, an LC filter is used to convert it into a pure DC form and we get the desired output voltage. In second case, Q2 is turned on for next half cycle and current will flow in this direction. Hence L2 will get charged, L3 and L4 will get charged too. But the direction of current is reversed, hence diode D2 gets forward biased. The pulsating voltage at the cathode of the diode is filtered by LC filter and we get output voltage at this cycle again. Hence these two steps get repeated for every period and we get the regulated output voltage. And remember one point, that switches Q1 and Q2 should never be switched on simultaneously or else they will get damaged permanently. Well, this is the simple working of push-pull converter. Now let's see the waveforms. This is the waveform of switching frequency of the converter. This wave shows the Q1 current. This is the current of Q2 transistor. There is a gap between these two current waveforms. Well, there is a reason for that. We'll discuss about it while designing. When Q1 is turned on, the current across secondary side increases due to induced voltage. That means when Q1 turns on, diode D1 start conducting and when Q2 turns on, D2 conduct. And when both transistors are in off condition, as you can see here, the current does not fall to zero. There is some finite value present over there and it is decreasing continuously. It is happening because of stored charge in the inductor and due to that, diodes are getting forward biased and simultaneously core is resetting. And if you see the output current, it starts increasing when Q1 and Q2 are on and decreases while they are off. Considering some necessary design parameters, let's take an example for designing a push-pull converter. Input voltage will be 200 volt. We need the output voltage as 100 volt and load current will be 2 ampere. We'll decide the switching frequency as 50 kHz. The output ripple will permit is about 100 mV peak to peak and the efficiency, that is eta of the converter, will be 75%. First step is the selection of core and calculate number of turns. The equation for number of turns is dependent on operating frequency, peak flux density, that is delta V, and effective area of the core. Initially, we may select a core randomly and peak flux density for that core. The number of turns and wire size is calculated and it is compared with effective area of the core, and if it is insufficient, the large size core is selected and calculations are repeated again till this condition fulfills. First, we need to calculate the output power, which is equal to 200 watts. If we see this chart, we can select the core for the transformer. For this type of transformer, we can select the E-type ferrite core. While making a transformer, we use two E-cores of same size and connect them with this fashion. There comes a bobbin in between which provides insulation between core and wire. Hence, we can select the core EE424220. Then, we'll calculate the number of turns which are to be wound around the core by calculating primary and secondary number of turns. Well, we have selected the core according to our output requirement. We'll see the remaining design steps in the second part of this video. Till then, stay tuned. And if you have any questions, you may ask in comment sections. And hit the like button if you like this video. And subscribe to my channel so that you'll get the updates about my new videos. Watch my previous videos if you have any interest in technology, and I'm sure you'll definitely find some interesting information. And finally, thanks for watching.